is that Bohr said energy level, right? 1, 2, 3, 4. Good enough? Bohr said energy level. But we find out that not only is there an energy level, a size, and the size and the energy, but there's also energy associated with the way it's waving. And so an S is a simpler wave than a P is a simpler wave than a D is a simpler wave than an F. So as you go left to right from S, P, D, F, you're getting more complicated waves, you're getting more energy. So when these things fill up, this is why you need a diagram like this, they don't fill up all the ones, all the twos, all the threes, all the fours. It goes, there's a 1, there's a 2, there's a 2, there's a 3, there's a 3, there's a 4, there's a 3, there's a 4, there's a 5, there's a 4, there's a 5, there's a 6, there's a 4, there's a 5. See it jump? Okay? So you got to follow that order when you talk about the way they fill. Now we haven't used it for filling yet, so just understand what you're supposed to be able to do with this thing at this point is construct it and know how to interpret it as far as where do you start and where do you go. Okay? Now another good thing about this orbital filling diagram is you can figure out some things about capacities, which we're going to talk about next. So if I asked you something about like the fourth energy level, well, the fourth energy level would be those guys right there. If I asked you about the third energy level, it would be those guys right there. If I asked you just about P's, all the P's would be there. All right, so we can pull a few things out of this. Okay, so let's talk about electron capacities. Actually, I'm just going to say capacities because we're going to talk about electrons and orbitals. So let's just say capacities. Okay, my gas tank on my pickup truck has a capacity of 19 gallons. Okay, does that mean there's 19 gallons in it?
No.
No. What's it mean then? Can hold up to. So when we're talking capacities here, these are maximum values. You know, you can have 0, and you can have anything up into to those numbers. Now let's keep in mind here, an orbital can hold how many electrons maximum?
8.
No, not 8.
7.
No,
2. 4.
2 of 2 electrons. Now remember, when we talked about quantum numbers, okay, N is energy level, rho is subshellar shape, M sub rho is the specific orientation of that shape, like px, py, pz. And then the last one, the electron spin quantum number, is plus or minus 1/2. That's because what we're doing is when you say all 4 quantum numbers, the first 2 are right here. 1s would be like n equals 1, rho equals 0. This would be n equals 1, or n equals 2, rho equals 0, n equals 3, rho equals 0, n equals 4, rho equals 0, because s is always 0. This would be n equals 2, rho equals 1. N equals 3, rho equals 1. All the p's would be 1s, all right? So what that gets me down to is energy level. Now let's say we're talking here, let's say we narrowed it down to, say 3p. So energy level is 3. When I say 3p, or when I say 3 rho of 1, I'm talking about the collection of all the p's, right? When I say the next one, m sub rho orientation, I'm specifying which of these 3 shapes. So plus or minus rho. So this would be like -1, 0, and 1. So when I say the third quantum number, I've now specified an orbital. And in that orbital, it can hold a maximum of 2 electrons, and their spins can be plus or minus 1/2. Follow? Okay, so the collection of 4 numbers gives us that. Okay. All right, so let's see. So let's say n equals 1. We're going to list subshells that are present. Subshells. We'll list max number of orbitals. We'll list max number of electrons. So at n equals 1, what's the only subshell I have?
0.
S, or rho of 0. Okay. So the subshell, all we have is S. How many types of different s orbitals do we have at an energy level?
4.
Just 1. right? There's just a sphere. So one orbital, and that one orbital can hold how many electrons? 2. And it's no coincidence that on the periodic table here, in this first period, I've got 1, 2 atoms. Because that first period has only one energy level, it only has one S. Hydrogen has one S with 1 electron. Helium has one S with 2 electrons. Okay, now let's go down to N equals 2. Hey, Garrett. Okay, so now we have S. And what else do we pick up? P. So P, max number of orbitals for S would be 1. How many max for P? 3. You got PX, PY, PZ, 1 on each axis. So that's 3, so that comes out to 4 total orbitals in the second energy level. And I can fit 2 electrons, I said, in an orbital, so how many could I fit in 3 orbitals? 6 for a total of 8. And again, it's no coincidence that when I count across here, that this is 1, 2, 3, 4, 5, 6, 7, 8. And remember, Mendeleev put this all together before we knew anything about any of this stuff. And the reason that it's put together that way is because atoms behave this way because of this stuff. He just didn't know that. He just looked at their behavior, how they reacted with things and stuff like that. All right, N equals 3. I'm going to have S, P, and now what do I pick up? D. Okay. You have 1 kind of S orbital, just a sphere. You have 3 kinds of P orbitals, which are PX, PY, PZ. How many Ds do you have?
5.
5. 0?
Did you get the 3 for the P?
Because you have PX, PY, PZ.
Oh,
PX, PY, PZ. And another way to say that is at energy level 2, N equals 2. Right? Rho can be equal to S or P, or it can be equal to 0 or 1. 1 stands for P. M sub rho is orientation. That's plus or minus rho. So it's plus or minus 1. So I get negative 1, 0, 1. Now for D, we just got done saying, what, 5 shapes?
Yeah.
We got 5 shapes because we have a D one way, a D another way, a D another way, a D another way, and then you got this goofy guy right there. Looks like the donuts.
What would that be? Would that be -2, -1, 0?
That's exactly it. -2, that's what my point was supposed to be. -2, -1, 0, 1, and 2. I don't care that you know which one correlates with which one because I don't even know. Okay, I'll be honest with you. Like when we say P, we have -1, 0, and 1. I don't know which one's PX, PY, PZ. All right, but it doesn't really matter though again because what's up? You know, it's like spin. What it's perspective thing.
Why doesn't it have a sphere for this level?
It does. N equals 3. We pick up D, so we have a sphere. We have 3 bilobes and 5 of these quad leaf or whatever they are. All right, so we have a total of, what's that, 9 orbitals? And that would be a total of 2, 6, and 10 electrons for a total of 18. Now, something we'll get into later. When you get to the third energy level, and if you just counted these 2 and those 6, you'd say, well, that's only 8. That doesn't make sense. This is actually 3D right here. Thank you. So if we count this as 3D, this is 3S, this is 3P. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, just like it says up there. Okay, and then last one we'll do for now is N equals 4. And the reason I'm not going to do N equals 5 is if you look over here, wouldn't 5 have another thing here? Because there'd be adding a new shape. So we didn't list it. That would be 5G. And if you had 5G, there's no spot on the periodic table right now for 5G, for a 5G. And we'd have to go, let's see. So it would be the elements after the elements right here, of which none have been discovered yet. And even if they do get discovered, they're not going to last very long. They're very, very radioactive. We get so. The thing that holds the nucleus together is something called a strong nuclear force. Okay, and the best I've heard it explained ever is by a guy named Carl Sagan. And Carl Sagan said, think of it like little balls with little hooks. Now, in the nucleus, you have protons and neutrons. Neutrons don't really attract or repel anything, but the protons should be trying to push each other apart, shouldn't they? Positive charges, yet they stay together. And the reason is because if they don't get close enough, they just kind of their positive charges push apart. But if they can get close enough together, those hooks can engage. And the reason they call it the strong force is because it is strong, but it's only strong over a very short distance. All right? So when you start to get very, very, very big nuclei, like up at the end of the periodic table, it's getting so large that distance is becoming an issue for the the strong nuclear force.
Like Velcro,
Kind of like Velcro, yeah. And when it gets so big, it just kind of spontaneously rips itself apart. I should say pushes itself apart because of the charge. Okay, so n equals 4, we got, let's see, I got S, P, D, and F. I've got one S shape. I got 3 P shapes, PX, PY, PZ. I got 5 D shapes. It's the 4 clover leaves and the 1 donut-y kind of thing. And then how many Fs should I get? 7. See the pattern here? Okay, and so that adds up to a total of, let's see, 16. Thank you. And so that'd be 2 and 6 and 10 and 14. That's 32. And again, if I go to the 4th energy level, all right, so this is 4s, this is 4p, and we'll get this in notes later. This is 4d, this is 4f. So if I count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I screwed up. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And that's where we get the 32 from. So, that's all I really wanted to give you today as far as capacity.